So far, we've looked at how to compute the explicit value of a series, and we saw that you could do that whenever the series is telescoping, geometric, or some combination of the two. It turns out that for most series, though, it's really difficult to compute the exact value of the series. And so we're going to ask a less ambitious question now, which is if you're given a series, can you just tell whether or not the series is equal to infinity or a finite number? It turns out that that question is surprisingly difficult to answer as well. And so the next couple days, we're going to try and develop some tests that you can use to check whether or not a series is infinity or a finite number. And the first test that we're going to look at is called the integral test, and this is from section 10.3 of the textbook. And so the idea is that we're trying to figure out whether or not this particular sum of a sub n converges or not. And the way we're going to check it is by finding a positive continuous decreasing function, f of x, where f of n matches up with a sub n for all values of n. And so we're going to see a picture of what that looks like in just a minute. But if we have a function that looks like that, then the integral from 1 to infinity of f of x dx is going to converge if and only if the sum does as well. And the integral will diverge if and only if the sum does as well. And so in other words, the integral and the sum both have to do the same thing. They're either both infinity or they're both a finite number. And the way that we can justify this is by looking at a graph and comparing the series to the integral in the graph. And so I'm going to start by drawing an arbitrary series, a sub n, which is going to be a positive decreasing series. And so on the horizontal axis, I'm just going to have the integers, 1, 2, 3, 4, 5, 6, blah, 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 up to infinity. And then on the vertical axis, I'm just going to draw some dots which represent this positive decreasing series. And so the first dot is just the value of a sub 1, and then the value of a sub 2, and so on. And so now I want to connect this to some sort of function. And the function f of x in the integral test is really just a function that's continuous, but it connects all of the dots in my sequence. And so now what the integral test is saying is that we can compare the area under the curve f of x to the sum of these dots. And it turns out that they're very strongly related. And the reason why they're related is because the dots end up giving us a Riemann sum for the integral. And so if I consider the dots to be a left endpoint sum for my integral, then I can just draw rectangles starting on the left end of each one of these. And then that could go off to infinity. And first of all, you could see that the area of any one of these rectangles is going to be the width of the rectangle, which is always 1, and then times the height of the rectangle, which is going to be a sub 1, a sub 2, a sub 3, and so on. And so that means that the total area of all of these rectangles is just going to be the sum from n equals 1 to infinity of a sub n. That is my Riemann sum for this integral. And at this point, it's pretty clear to see that these rectangles are all on top of the function. And so that means that this sum is greater than or equal to the integral from 1 to infinity of f of x dx. Okay, so that's one relationship I can find. But it turns out that I can find another relationship between the sum and the integral if I consider a right Riemann sum instead. And so at this point, I'm going to draw rectangles again. But the rectangles are going to use the right endpoints here. And so if I do that in this pink right here, then you can see that the area of each of the rectangles is still dependent on some a sub n value. And it's also, all the rectangles still have width 1. And so first of all, this new Riemann sum is certainly less than the integral. And it's still going to be the sum of some a sub n values, but the first rectangle right here uses the a sub 2 value. And so now this is the sum from a sub 2 to infinity. And so now we can squish our integral in between two really closely related sums. And it's not hard to see that the sums on the outer part, they either both converge or they both diverge, because the first term in the series, the a sub 1, doesn't make a difference. And so if my sum, a sub n, converges, then that means that it's pretty small, but the integral is smaller than that, and so the integral has to converge as well. On the other hand, if my sum diverges, then this part on the right has to be infinity, and that means that the integral would have to be infinity as well. And so either way, these inequalities show that the integral and the sum have to do the same thing. Okay, now let's see how we could use this in an example. And so here, let's say that we're trying to compute whether or not this sum of 1 over n to the p converges or diverges. And so 1 over n to the p, that matches with the function f of x is equal to 1 over x to the p. Right? And that's definitely a positive decreasing function. And so that'll be positive and decreasing as long as p is greater than 0. Okay, and so now that means that the sum does the same thing as the corresponding integral. And so that's the integral from 1 to infinity of 1 over x to the p dx. But this is an integral that we already looked at when we talked about improper integrals. And we know that this integral converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. And so that ends up giving us a corresponding rule for series, which is that a series of the form 1 over n to the p from n equals 1 to infinity is going to converge whenever p is greater than 1, and it's going to diverge whenever p is less than or equal to 1, which is exactly the same as we saw for integrals of the same form. And we're going to use this test a lot, and whenever we use it, we'll just say that whatever we're talking about is true by the p-test.